What's up? Do you know what this is? We're going to make this. This is a sphere with 100 particles in it acting as an ideal gas. So we want to make an ideal gas model using actual balls in Python. I'm going to go through all the steps. Let's get started. Whoops. Okay. Right there. So let's start with the ideal gas law. I'm not going to go into all the details. You've probably seen this PV equals nRT in this equation. Before I forget, in an ideal gas, I'll probably say this again later, in an ideal gas, the particles do not interact with each other. So it's pretty easy to model. P is the pressure, V is the volume. N, in this model, N is the number of moles of gas. So it's a measure of how much gas you have, but it's the number of moles. R is a gas constant. Don't worry about the value of that. And then T is the temperature. Now, there is the physics version of this, PV equals NKT. In this case, P is the pressure, V is the volume, N is the number of particles, and K is the Boltzmann constant, and T is the temperature. So how do we model this? Well, the first thing is we need to somehow have a gas ball, interact with a wall. So here's a sphere. Why am I using a sphere? Well, I'm using a sphere because a sphere has one wall. If I want to make a cube, I could do that, and it wouldn't be that difficult. But I'd have to have interactions with this wall, then that wall, the top wall, the bottom wall. There's 6 walls in a cube, and I don't want to deal with that. This is just one. So I have a sphere of radius r. And we don't really care about the units too much because, I'm going to have a 1 meter sphere, but if there's only 100 balls in there, it doesn't really matter anyway. So it has a radius of r. Now, when a gas ball, kind of penetrates into the surface, when the center of the ball goes further than the radius of the sphere, and we can call that position the vector r, lowercase r, then there should be a force pushing back towards the center. So we can model this as though it was a spring, right? If that ball goes greater distance away than capital R, then there's a force pushing it back towards the center. I can do that, and I can use the standard equation for the force due to a spring. And it's not the normal Hooke's law you'd think about because we need a real version. This is the version that we're going to use. Here we have K is the spring constant for the wall. You make that whatever you want. This is the magnitude of that distance, r, the vector position, which is going to be greater than r, and that's the scalar value r. And this is going to give me how much it gets pushed into it, right? So that's your Ks. And then I have this r hat, and I need that because that's going to be a unit vector pointing away. The negative sign makes a vector pointing towards, and that gives me the direction of this force as a vector. And so now I can glide in this way or up or down anywhere, right? And it will push back toward the center. So that's pretty cool. Now, to do a numerical calculation, we're going to use the Euler method, and I want to go over the steps. Hopefully, you've already seen this before. I'm not going to spend a lot of time on this. So the main idea is to break the motion of these balls, or just one ball, we're going to start with just one ball, into short time intervals, and I'm picking 0.001 seconds. It doesn't really matter. So during that time interval, I can calculate the net force in the object. So that net force for one ball is going to be either 0, because it's in the center, or it's going to be that force that we just calculated when it interacts with the wall. Okay, so I can calculate that. Once I do that, once I have the net force, I can use the net force to and the momentum principle to find the change of momentum. So the momentum principle says the net force on an object is the rate of change in momentum. Okay, and I'm not going to write it as a derivative because we have a finite time difference. And momentum is mass times velocity, a vector. That's important. Now, if I take this, I can actually write the change in momentum as P2 minus P1, where P2 is the momentum at the end of the time interval, P1 is the momentum at the beginning, and I can get this. So if I assume a constant force, I can say that the final momentum is based on the momentum before plus the force times time interval. That just comes straight from there, assuming I only have the net force. Okay, so we're going to update the momentum. Now, I can also assume that the momentum's constant, which is kind of silly because I just changed it. And I can use that to find the change in position of the ball. And this is really important. I can go through all the time intervals, and I can just keep going through, calculate the force, update the momentum, update the position, and do it again and again and again for as long as I want. Okay, so that's the main idea of the Euler method. Super useful, super easy to implement in Python. I am going to use WebVPython. So there's actually two common ways you're going to see this. You can go to glowscript.org, which is WebVPython, or I'm going to actually be using trinket.io just because it's easier to share. And I will put the links to the code down below, so you will have that. VPython is a module for Python that does 3D models if you haven't seen it before, and it's super useful. It's what I made that first animation in. So, and it has functions for graphing and a whole bunch of other stuff. The nice thing about GlowScript and Trinket.io WebVPython, and they like to call it WebVPython, which is fine with me. But it runs in a browser and it even runs on your phone, so that's kind of cool. And I already said I was going to give the link down below. Let's just jump into the code. I'm going to break this into small pieces of code. I'm going to go over each part and explain it, and then we'll do some cool stuff. So this is the first part of the code, and up here I'm just declaring some constants. Now again, we're doing a numerical calculation. We need numbers. Okay, we don't need to put the units in there, and I'm having bare bones code just so it's easier to see. You can add this and make it spicier if you want. But this is the radius of my sphere, 1. That's the mass of each of my gas particles. So that's really heavy, right? 100 grams. And you really can make this whatever you want. It's just going to change the scale of the plots and stuff. But I want to see how these things change. It doesn't really matter what they actually are. K is that spring constant, the interaction between the wall and the ball. And you can try changing that. That might need to be higher. I'm not really sure. Time 0. And the time step too. You could try changing that. These are things you can try to change and play around with. This right here, shell, is my container. It's a shell. And it's an object type of a sphere, which is built into WebVPython. You'll notice this is an actual real Python. I don't have to pull it from a module. The whole thing's already loaded. So I don't have to say what module it's from. You can run this in real Python, but I'm not. So the sphere has different attributes you can assign. The position, so I'm giving this sphere the position of the center of the sphere is at the vector 0, 0, 0, so at the origin, and then it has a radius, and then I'm making it transparent with this opacity equals 0.3. So opacity of 1 is solid. I just realized it's not a shell, it's actually a full sphere, but it works fine. Now B is, I'm making one ball. Right, so B is my one gas particle, and it's also a sphere, but it's much smaller. You see I have a radius of r over 40, and I gave it just some random location, r times this vector, just to put it somewhere. And I made it yellow. I gave it color equals color.yellow. You can make it have a trail, which I put in the animation I'll show you, but you don't have to do that. Then I need to give it and if I want to update the momentum, I need to start with the momentum. So here I'm going to give it a velocity of 2, and I know it has a mass, and then I just give it a velocity in some random direction. So right here, this random is a random number generator in WebVPython, and it gives you a number between 0 and 1. So if I say 2 times random minus 1, that's going to give me a number between negative 1 and 1. So this is just, it doesn't actually give me the same velocities, but it doesn't matter. And then I multiply it by the mass, and I get the momentum. Okay, and we'll talk about some other random numbers later. Now for the main loop, I'm going to go through this, do those calculations, calculate the force, update the momentum, update the position, as long as time is less than 5. So this is going to be 5 seconds. Now this statement right here, rate 1,000, since I have a time step of 0.001, rate of 1,000 says don't do this loop more than 1,000 times a second, and that will make it run in real time. Okay, so if you want to make it run in slow time, you could put 500. That would run it every it'd be half time. If you want to run fast, you can make the number higher. This r equals b.pos. B.pos is the vector location of the ball, and I'm going to call it r just so I don't have to talk about b.pos, but they're the same thing. And then this line right here, I'm going to set the force on the ball equal to 0. Because if I change it, if it's colliding with the wall, then I need to calculate what that is. But once it leaves the wall, I need to put it back to 0. So every time at the beginning of the loop, I'm going to set the force to 0. And now this line right here, 21, this just says, is the ball into the wall, right? That's what that says. And if it is, then calculate the force. Now I can use that to update the momentum. I can update the position. And this is really nice. B.POS is the position of that sphere. If I change that, it'll move that gas ball around. And then update time, or I'll get a loop that goes on forever. So this is what it looks like. This is the actual code in Trinket. I run it, and there you can see the ball bouncing around. And then we can rotate this around, which is kind of nice. One of the things that I thought was wrong is that you always run it, it's going to end up moving in a plane. But it's because it's a central force, right? The force is always pointing towards the center of the sphere. So that makes angular momentum conserved. And so it makes it move in a flat 2D plane. Okay, but there you go. That's one ball. But if we can do one ball, we can do many balls, and that's what we're going to do. To do many balls, we need to use an idea of Python lists. So this is my smashing quick tutorial in Python lists. I have another video on this, but here's my super quick lesson. So I can make a variable called stuff and assign it to as an empty list with square brackets. So that's a list, okay? And it's not a NumPy array, if you're familiar with that. It's just a list. And then you can add things to the list, right? If I do this, stuff is stuff plus the bracket 1 is going to add the number 1 to my list. And then I'm going to add the number 4 and then 9. You can do whatever you want. And there's other ways to add it. That's just the way I like to do it. And if you print that out, you just see, here's my list, 1, 4, 9. Yay, isn't that awesome? Now, how do you use a list? If I go through and I want to use the numbers in the list, what if I want to add up those numbers? This is a very important thing right here. I have just a starting number total equals 0, and I can go through each element in the list with this 4x in stuff. It's really useful. So this is just going to go through the list and call each item in the list x. So in this first, it'll be 1, right? And then I'm going to add that to the total, and then I'm going to go to the next one. I'm going to call it x. So I'm going to, this plus x is that number in the list. And when you print it out, you get 14. Pretty cool. Okay. Because I don't have to just put numbers in a list. I can put spheres in a list. I can make a list of gas balls. So here's how you do that. I'm going to start with, this is the way I like to do it. There's other ways to do it. This is the way I like to do it. Okay. So here's my lowercase n. I use my counter. Capital N is my maximum number. I want to do 100 balls. So this loop right here, while n is less than n, just goes through and makes 100 balls. And you can see here I add 1 to n. Not always, but I sometimes do. I have my list of balls. I call it BS for balls. I didn't want to put balls. It was too much to type, so I just put BS. It's an empty list. Now, I want to make 100 random balls in a sphere. So I'm going to use that same random thing. So the first thing I want to do, remember my sphere is a 1 radius. So it goes from positive 1 to negative 1, the x direction, positive 1 to negative 1, the y direction, and so forth. So the first thing I'm going to do is to generate a random vector right here that goes between x goes from negative 1 to 1, y goes from negative 1 to 1, z goes from negative 1 to 1, and r is just 1. Okay. Now, some of those points would be outside of my sphere, right? Because I could get the point 1, 1, 1. That's not in my sphere, right? I want to only include the ones that are inside a sphere, and they would be inside a sphere if the magnitude of this temporary vector RT has a magnitude less than 1. So I'm going to check, is that magnitude less than r? Then it would be in the sphere, and I'm going to make a ball. And so I'm going to add 1 to my n, my counter, and I'm going to make my ball. As a sphere, I'm adding it to that list right there. So to give it a color, give it a radius, and its vector location is that random number. So you see how I do this. If it's not a valid position inside of a sphere, I just do it again. But I don't count it, right? I only count it if I make the ball and add it to the list. Okay, so what do we have next? Now, the other thing I'm going to want to do is to give all of the balls random velocities. But in a gas, the velocities don't have just a uniform distribution of velocities. You could do that if you want. Instead, they have a normal distribution. So we need to make a normal distribution function generator, which we don't have in WebVPython, so we have to build it. So this is the Box-Moeller transformation. I looked it up. And the idea is to first generate a random number between 0 and 1. I'm calling it U1. That's what Wikipedia calls it. And then another random number between 0 and 1. And from that, I can generate a random normal distribution, z1, by taking the natural log of u1, it's a random number, multiplying by -2, and then taking the square root, and then multiplying by the cosine of 2 pi times the other random number. That's just a formula. And here's what that looks like as a Python function. So I'm going to have a normal function. I'm going to give it what I want the average to be, and what I want the standard deviation to be. And then I'm going to generate my two random numbers, u1 and u2. Random just gives you a number between 0 and 1. That's it. And this will generate a random velocity, vt. But it won't have the right average, and it won't have the right standard deviation. So I can shift it to the average. This will have an average of 0. I can shift it to the average by adding that average, and then I can give it the right standard deviation by multiplying by the standard deviation. And then it'll make it right. Okay, and then I return that velocity. Nice? Okay. So once I have my list, I need to set my initial momentums for all the balls, and here's how I do that. So this is V0 is my average velocity, and then I just go through B and BS, which is the super nice way of doing it, right? I can just refer to B as though it's an individual thing, although this makes it go through all those balls in the list. It's pretty cool. So right here, I'm just going to create a velocity using that normal function I just made. I'm going to give it my average velocity of V0, and I just picked a standard deviation of 0.3. That's something you can change and play with. And then its momentum, BP, B.P, is just the mass times the velocity right there. And then this is in a random direction. That just gives me my magnitude. This is my random direction right here. So I'm going to pick a random vector between -1 and 1 for all the x, y, and z components. And then I'm going to take the norm, return to unit vector. So this will have a magnitude of 1. So I will get the correct velocity. Okay. And then I need to set the force for each one also, which is kind of weird, right? We think of the force as the interaction between the wall and the ball, but this is really the net force on that ball. It's a really easy way to keep track of all the forces, and I use it for other methods too. Now I can make my loop. So my loop looks like this. It's the same as before, right? Except that I'm not going to do this B.P and B.POS is in my for B and BS loop, right? So I'm going to go through all those and do the same thing. But other than that, it's the same, right? Which is really kind of nice. And here's what it looks like, I think. Yeah. There you go. Cool? Okay, that's 100 balls. Now, if we want to do the ideal gas law, then we need to measure the temperature, right? How do I measure the temperature of 100 balls? So the kinetic theory of gases says that the average kinetic energy is 3/2 kT, where K is Boltzmann constant. So I can use that to calculate the temperature if I can measure the average kinetic energy. And I'm not going to actually use the temperature because this is a super small number and it'd really look weird, especially for just 100 numbers. I'd rather just calculate the kinetic energy and say it's proportional. That's what I'm going to do. To do that, I define a function that calculates the average kinetic energy. So I give it my list of balls. I call it BB in the function, and it returns the average kinetic energy. So I just take my list BB, and then I start with the total kinetic energy of 0. I go through each element in the list and calculate. This calculates the kinetic energy. It's momentum squared over 2m, but I got to take the magnitude, remember, because momentum's a vector. So magnitude squared, and then divide by 2m, and then add it to the total. And then I need to divide by the number of particles. So I could use n, I really could, but just to make it generic, the length of BB tells me how many items are in that list. So if I divide by the len BB, it will return the number in there, and then that will work. Okay, so let's do this. Let's do that. Let's run it for 5 seconds and plot the kinetic energy as a function of time, and we get this. It's not constant. It's constant, right? It's not exactly constant. So why does it go up and down even though the average is around, it should be at 0.2, right? Because I have a mass of 0.1. 1/2 times 0.1 times 2 squared is 0.2. So what happens though, I'm counting all these balls in that sphere, and some of the balls are colliding with the wall at any given instant, so they could be going slower or they could even be stopped. And so in that case, whenever they're colliding the walls, they don't really have the correct average velocity, but they're counted. And so that's why this fluctuates up and down. The more particles you get, the greater the ratio of particles inside the sphere to the ones interacting with the surface, and would give you a better value. That's only 100 balls, okay, so you expect it to do that. What about the pressure? How do we measure the pressure? Well, the pressure, it's an ideal gas. It doesn't have internal pressure. It's only the pressure as it exerts on the container. So if I calculate the force on the wall of the container and divide by the area of the container, that's all I have to do. So here you can see I give it two things. I pass two things. I give it the list of the balls and the radius of the sphere so that I can change that radius. Again, we're going to calculate the total force. To calculate the total force, I just go through my list of balls and add up the vector forces. Now, I only want, if I add up the total vector force, it could be 0, right? Because pushing this way, pushing that way, I want to calculate the magnitude of the force. And they're always pointing towards or away from the center because of the way I calculate that force. So I don't have to worry about weird things happening. So I just take the magnitude of the force and add it to the total, and that gives me my total force. I calculate the area, 4 pi r squared. I thought I made a mistake. No, that's the area of a sphere. And then I return F over A. The pressure is force divided by area. And if we plot that as a function of time, it looks like this. Again, we get some non-constant stuff, and that's okay. What's happening here is that, we're only counting the interaction with the surface. It's possible that at some given time, none of the balls could be hitting the surface, so the pressure would be 0. So this can drop down to 0. But we get some average value, and it seems to be reasonably well behaved. Well, we can measure pressure, we can measure volume, we can measure temperature. So let's do some PV equals nRT stuff. What would happen if I take my sphere and shrink it? Let's do that. Here's what it'll look like. It's not super fast. So all I'm doing is, in my loop, I'm changing the radius of the sphere. I'm decreasing it by a constant value, which isn't a constant rate of volume change. I just realized that, but it doesn't matter as long as I shrink it. Okay. So you know that if you take a container of gas and you decrease the size, the pressure should increase. Okay. What about the temperature? Well, we like to think the temperature increases too, and they both increase here. The kinetic energy, if you just take a gas and I have a sphere of 1 radius and I let it go, I know what the kinetic energy should be. Now if I start from scratch with the same gas, but in a smaller sphere, it should also have the same temperature, right? Because that's dependent on the initial kinetic energy. I think the kinetic energies, the temperatures and kinetic energies increasing because as the wall smashes, I have a picture here. As the wall smashes, imagine this wall is moving in. It's going to exert more force in the direction of motion than away from the motion. So overall, it increases the speed of the thing. I think that's my explanation. I'm not 100% sure. And if you want to fix it, you can fix it. But I can look at what should be constant. This, if I solve for PV over T, all those things change, but Rn does not change. So PV over T should be constant. So I can calculate PV and T. I'm technically doing kinetic energy, right? Okay. And if I plot that, you can see it stays fairly constant. Much more, this is clearly increasing in pressure, right? And the temperature increases really nicely. So, but that increases, does not increase and stays constant. So I think things are working well. But I'm going to put the link to these codes down below. You can play around with it to your heart's content and change things, and you should. And it's great fun to build a model. Also, in this model, I actually use 1,000 particles instead of 100. Try increasing your number of particles. See how high you can get. Just, see how far you can go before you break it. Things might get slow, but that's the fun part. Okay. Ideal gas law, Python, particles. Hope you like that. Later.